All right, let me start off this video. Since while we're talking about mercury, I would like to start off by doing a quick calculation. This is exactly the way I do this. If somebody was in the classroom, a student was in the classroom. All right, so anyhow, the mass of mercury is found to be 3.3 times 10 to the 23rd kilograms. Its radius is 2,439.7 kilometers. Find the density of mercury in grams. That should be grams per centimeter cubed. I couldn't do the superscript, but that's so the density is going to be grams per that caret key just means raised to the third power. Anyhow, round to one place past the decimal. Okay, so here we go. All right, so we take, well, first of all, notice the mass is, the mass right here is given to us in kilograms. And so we want the mass to be in grams. Let me just state right over here that, of course, the density, all right, this thing that we call rho, is the mass divided by the volume. And the volume of any sphere is, I'll write it out in just a moment, but it's 4 times pi divided by 3 times its radius to the third power. Right, so what we're going to do right now is we're going to concentrate on the mass, and we're going to get the mass into grams. And then we'll calculate the volume in centimeters cubed. Centimeters to the, sorry, that's supposed to be a 3. That doesn't look good at all. Sorry about that. Here, let me erase that. All right, so centimeters to the third power. Sometimes it's hard to do that. All right, anyhow. All right, so we take the mass, and the other thing is, of course, you got to know the conversions, right? So 1 kilogram, right, 1 kilogram is, of course, 1,000 grams, right? So, which can also be written as 10 to the third. Whoops, that's a 3. Sorry, 10 to the third grams. All right, so we're going to use that fact to convert this. All right, so here's our mass. Is 3.3, times 10 to the third. I'll just write it like this. It's just easier. 10 to the 23rd, E 23rd, which of course means 10 to the third. And of course that's kilograms. And then the way we do a conversion is 1 kilogram is 10 to the third grams, right? So I'm going to put 10 to the third grams, and this is 1 kilogram. 1 kilogram, and so the kilograms cancel, right? And so 10 to the third and 10 to the 23rd adds up to 10 to the 26th, right? Because you just add the exponents when you're multiplying and you have the same base. So this becomes 3.3 E, capital E, 26. All right, so, and that's grams. All right, so this is the number that we're going to use right here in the numerator. All right, so now the volume is more complicated. So the volume, what we have to do here, of course, is we're going to have to change, and this sometimes is a little confusing. So we're going to change the radius from kilometers to centimeters. All right, but of course it's the same procedure. All right, so here we go. The radius is 2,439.7, right? And right now that's kilometers, and that's a decimal point. That's supposed to be a decimal point. It's kilometers. And then basically what's going to happen is it'll change into that same number, this 2,439.7 times 10 to the 5th centimeters. All right, so here we go. Here's the proof of that. All right, so kilometers, and then of course there's 10 to the third meters in 1 kilometer. All right, so the kilometer part cancels. All right, and then God. So that so that's meters, and then we know that there are 100 centimeters. So that's all. That can be also written as 10 to the second. Sorry, that's a two. Here, let me erase that. That doesn't look very nice. Um, 10 to the second centimeters. 10 to the second centimeters in 1 meter. All right, so the meters cancel, the kilometers have already canceled. So see, it's the same number, and you say times 10 to the third times 10 to the second. So this becomes, 2439.7 E5 centimeters. All right. All right. So that's and now we can do the volume, right? So the volume is equal to 4 pi. It's always 4 pi divided by 3. The volume of any sphere, okay, is, and then you take the radius, radius raised to the third power. And so this is the radius that we just figured out, 2439 point, what is it, point 7, sorry, 0.7, I saw that 5 and got confused, 0.7 E5, right, and of course that's centimeters. I'll put that in there just for the heck of it, and then you raise that to the third power. All right, so let's go ahead and do that. Have a scientific calculator right here. All right, so 27. Oops, I already messed up. 24. 39. 24. 2,439.7. All right, and then E to the fifth, right? So that's the number of centimeters. That's the length of the radius in centimeters, and then we have to raise that to the third power. Hold on, let me remember how to do that in this calculator. You hit the X to the Y button, raise to the third power. All right, and so this is what this is going to equal. All right, so it's I'm not going to write that down yet. It's going to be easier to write it in scientific notation. And so it's say times 4 times pi. There it is. And then divided by 3. All right, so there. All right, so it's 6.08. Okay, so here I'll do it this way. So I already know that. I mean, this calculator is it's not putting it in scientific notation, but you can count the each comma. There's 3. Anyhow, it's 6.08 times 10 to the 25th. Okay, so that's basically what this is. 6.08 times 10 to the 25th. And that's, of course, since we cubed the centimeters, it's cubic centimeters. So now we take, we're going to take this number the mass that I circled earlier, this mass right here, and divide it by this volume right here. All right, so that's already in my calculator. So I'm just going to, where's my calculator? Right there. All right, so here's my calculator. So I'm going to type in 3.3 times 10 to the 26th, right, and divide by this number. Oh, yeah. With this calculator, you got to store that number. All right, so here, I'm going to put that in storage just to make sure. All right, so anyhow, it is going to be, it's 3.3 times 10 to the 26th, exp 26 divided by, all right, so what I just put in storage, so memory recall, it's however your calculator remembers that. All right, so there it is. So that's the actual, so we're going to round it to, as it says up here, round it to one place past the decimal. it'll be 5.4. Okay, so 5.4, right? So here we go. So the density here, I'll just write it down here. The density, which is what we calculated up here, is 5.4 grams per centimeter cubed. All right, so just to remind you, all right, so that's the density of the planet Mercury. Um, that's actually really close to the density of the Earth. And keep in mind, the Earth is much big. It's like 3 times bigger than Mercury. So that tells you that there's whatever the density is, you, since the density is so similar, that tells you that Mercury has a lot of iron in it. Right? That's the lesson here. Okay, this tells you about the internal structure of Mercury. All right, so that's why we got to be able to do these calculations. All right, so let me continue here from current slide. There we go. So as I was mentioning before we did the calculation, we've got this thing called Caloris Basin. That's an important feature on Mercury. We'll actually see a better picture of it in just a minute. All right, let's see. So unlike the moon, where they are found almost exclusively in the Maria, the lava flows are found in many of it's all over the surface. All right, so where we, yeah. So anyhow, that's all right. So there's an example on the surface of Mercury. These are for the most part shown in false color. They add you add color to bring out the features a little bit better. All right. Anyhow, we do that electronically, generally just to get a sense. But there's volcanic vents. There are other areas where the lava has broken through, and they think it's notice they say in quotes recent times, within the last billion years or so. That's if you consider that recent times. There are so this is a huge feature that you find on Mercury. All right, so there are these giant cliffs. I mean, huge cliffs all over the surface of Mercury. They're called so geologically they're called scarps. All right, so please remember that term scarps. And so basically, how did the scarps form? And we really didn't know for a long time. We knew that the scarps were there even back as early as 1974 when Mariner 10 went by. We knew that there were these scarps. But what it turns out that we think that they occurred because Mercury, especially the internal parts of Mercury, either its mantle or its core, shrunk suddenly. And when it shrunk, it's kind of like if you had a grape, and as time goes on, and you just left the grape in the sun, right? It becomes like a raisin. It shrinks, right? It shrinks, and that's how we think these scarps occurred. There are multiple features on Mercury that show that there were impacts. This one is a little bit more famous. It gets the name the spider because of the features, the way the features look. There's Caloris Basin. Okay, so this is huge, right? 1,300 kilometers across. This was so intense that it almost broke the planet apart, and we think that it appeared about 3.8 billion years ago. So remember that Mercury formed same time that the rest of the solar system formed, about 4.5 billion years ago, and this collision, which was with a huge object almost broke the planet apart.